exam is not just Wednesday.
That's why everyone can be chill about the midterm. I'll give you a detailed list of what will be on the midterm, right? And I'll have that posted by. Are you recording? Yes, you're recording. Okay, great. So yeah, we've been going maybe not at the ideal pace, but we will. So midterm exam next Wednesday, and by this evening or tomorrow, I'll have a list of what's going to be on the midterm. It's in class. I won't be here, but Cody, who's my grader, will be here to run it. There is one more person in the class. Do we ever see them?
I think they come last week. Yeah. During the
Came for the VASP tutorial.
yes.
So my teaching is not good enough. Come to class. Okay? If you're watching this, come to class. Show up. Okay. So today, let's go to compound. So was the VASP tutorial useful? Actually, by the way, it may end up being the most useful thing that you'll take away from this class. So today I'll have like a homework on using VASP to draw structures, right? All of you have installed it, yeah, and it works well. Did Matt show you how to enter a new structure, and he also showed you how to open a CIF file, how to make bonds, how to make polyhedra? Well, okay. I mean, the sort of maximum extent of VASP use keeps growing, right? It's a research tool, but it's a great learning tool for crystallography. And sometimes how you should play with it is actually just messing around with it. For example, if you take the cesium chloride structure, PM3 bar M, you take the alpha polonium structure, PM3 bar M, put polonium at 0, 0, 0, and then just see what happens if you move polonium from 0, 0, 0 to something like 0.100. And you will find that you're creating at least 6 replicas of polonium in the unit cell. Right? So you learn how crystallography works by playing with VASP. Did I say VASP? I meant VESTA. Sorry, that's a figure of speech. So today we are ready to look a little bit at the structures of compounds. So we looked at the structures of elements. We've done alpha polonium, which is simple cubic, alpha iron, which is body-centered cubic, copper, which is face-centered cubic, and then we also looked at magnesium, which is hexagonal close packed. We looked at graphite, which is the same space group as magnesium, but it has an extra atom. And then we looked at silicon, the diamond structure. So those are all pure elements. There are other pure element structures we could look at, but we don't look at them for 2 reasons. One is they don't occur commonly. For example, boron has an extremely complex crystal structure. Okay, there's one particular form of boron called a rhombohedral boron 105, and that structure has 105 boron atoms in the unit cell, like crazy. And you may ask, why is boron so complicated? And that's actually a good question to ask, and it's not a simple one to answer. Manganese is also quite complicated, surprisingly. Some of the structures of manganese, which is in the middle of the periodic table, in the middle of the transition element, so it's surrounded by FCC and BCC, but all of a sudden manganese says, I want to be different, okay? And that difference in manganese is intimately linked to its magnetism. So some elements can surprise you. The main group elements do all sorts of things, phosphorus, sulfur. These things are not representative. They take all kinds of different structures, so we won't go through all of them. So today, let's start looking at some simple binary structures, like compounds, okay? But before we do that, I want to go through a set of rules that were laid down by Linus Pauling in 1928 or 9. I'll actually link you to the paper from Linus Pauling. And you know who Pauling was, right? What do we use of Pauling's? We use the idea of valence bonds, valence bond. We use resonance, right? And we've already looked at resonance in the structure of benzene. All of this came from Pauling. And we look at, what else? We look at electronegativity. Pauling defined electronegativity. Well, Pauling also in the 1920s came up with rules for crystal structures. And it should be pointed out that these rules really apply often mostly to the structures of cations with electronegative anions. So more like ionic crystals, ideally for ionic crystals. Okay, that's what we want to talk about. So what are these rules? I'll go through the rules, and as I go through the rules, I'll give you some definitions. Okay? So the first rule of Pauling is called the radius ratio rules. And by the way, Pauling wrote down these rules, I think 1929, 1928, 29. A few years ago, some people, actually I know one of them, wrote a paper saying, oh, we've used like machine learning to look at Pauling's rules and we find that these rules don't work very well, right? So what do you call that when people say Pauling's rules are stupid? What's the title of the paper? What kind of a title is it? It's clickbait, right? But actually, if you look, I went and looked at that paper, and I think they've misinterpreted. Firstly, they've misinterpreted. Well, firstly, I should say, if you're writing a paper in the 2020s about Pauling's paper in the 1920s and saying Pauling was wrong, it was 100 years ago, almost, right? But the second thing is, when I looked at that paper, they have made mistakes in applying the rules. So this is often the case with these large ML papers. You can never actually look at specifics. But I saw 2 examples which they mentioned, or 3. All of them are either a misunderstanding of the rules or a misapplication. So anyway, these rules are pretty sound if you're working on oxides. And when these rules fail, there's some science to be learned. Okay? But the first rule of Pauling is called the radius ratio rule. And you're probably familiar with this radius ratio rule. So it says the distance between so these are for salts. So we are always looking at cation-anion pairs. For example, sodium chloride, we are looking at a sodium and its neighborhood of chlorides. So distances are sums of radii. This is almost like if you have a cation and an anion, you have an anion radius and you have a cation radius, right? The distance is RC plus RA. Okay? And this is not only obvious, it's actually circular, because the way we assign distances is we measure the total distance experimentally, and then we apportion the distance, and we say this much comes from the cation and this much comes from the anion. Right? Does that make sense? And I can go through the history of how this was first done, because if you have a whole bunch of distances, you have to fix at least one in order to get the other distances. Yes? And the way the original people did it, a guy called, in the early part of early days of crystallography, is they took lithium iodide. And they said, effectively, the distance between lithium and iodine is effectively the radius of iodine. Lithium is so small that you can assume that it's the radius of iodine. So that fixed, and as soon as you fix one radius, you can self-consistently go in and fix the others. So the distance is the sum of the radius, but the coordination, which means 4, 6, 8, etc. What is coordinators? How many anion neighbors does every cation have? How many anion neighbors per cation? That's called the coordination number, right? And when we've looked at elemental structures, we've been talking about the coordination number. Simple cubic is 6, body-centered cubic is 8, face-centered cubic is 12. So this is an important consideration. The properties change, the mechanical properties change, the density changes, a lot of things change depending on the coordination number. So certainly the electronic properties. So the coordination number, actually it can even be 2, 3, 4, 6, 8, etc. The coordination number depends on the radius ratio. And I'm sure that in your undergraduate years, you have seen you've had some exposure to this radius ratio rule. You've had some exposure to the radius ratio rule. If you have a very small cation, then it doesn't want a lot of anion neighbors. If you have a very large cation, then it wants more anion neighbors, right? Have you come across this? Are you familiar? Do I have to spend some time on this? Give me a thumbs up for the radius ratio rule. Maybe you'll remember it if I give you one example. I'll give you one example, but I won't go into much greater detail because I want to move on. The fact that I inverted by the way, my inversion, was it helpful at all? Was my showing E versus K diagrams at all helpful for 200B? It was, okay. Because that's why I did it. Even though I think a more natural evolution is to show crystal structure before talking about electronic structure. So radius ratio, let's consider the case of octahedral coordination. Octahedral coordination. So an octahedron looks like this, right? That's an octahedron, yes? And you have a cation that's in the middle of all these anions. And remember, anions are larger than cations. Are anions larger than cations? Yes? Yes or no? Which is larger? Chlorine minus, Cl minus, or sodium plus?
Or sodium, because if you take away an electron, the effective charge goes up, and then the electrons.
So sodium is smaller.
Yeah.
You take an electron out, then there's one more proton in the nucleus than there are electrons. So every electron feels a positive charge that pulls it towards the nucleus. If you take chlorine and add an electron, that electron repels all the other electrons that are already there, and it breathes outwards. It becomes bigger. So here are the anions, and here is the cation in the middle, right? Here's the cation in the middle. So I can take this plane here. I can make many planes, but I'll take this plane here. I'll take this plane here and write the plane like this. And in this plane, I'm going to have, the assumption is that the anions actually touch each other. The anions look like this in this plane. And it's generally a good assumption. Okay? And the cation looks like this. If it fits ideally. Ideal. That's the ideal radius ratio. Who wants to do a little math? Shall we do a little math? And I can assure you that I always struggle with this. I always struggle with this. Do you agree that the base of this triangle, if I take this triangle here, the base is the radius of the anion? The hypotenuse is the radius of the anion plus the radius of the cation. And this length is the same as this length. What's the triangle called where two sides are equal? Sorry? Isosceles. It's isosceles. So for this triangle, if you apply Pythagoras, apply the right angle theorem, so RC plus RA squared is equal to RA squared plus RA squared. So RC squared plus RA squared plus 2RC RA is equal to RA squared, RC squared plus RA squared. Now, what we want is RC over RA. So we want RC over RA, right? Let me try and divide everything by RA squared. So RC squared over RA squared plus RA squared over RA squared plus 2 RC over RA squared is equal to RC squared over RA squared plus RA squared over RA squared. All right.
Why on the right side is RC squared plus RA squared? They should be like 2 RA squared.
Oh, that's right. Sorry. RC squared. Thank you. RC squared, RA squared plus RA squared. Thank you. I thought there's something wrong. RA squared plus RA squared. Yeah. Thank you so much. Yeah. See, I already made a mistake. Good. 2 RC squared over RA squared. Okay? So I can cut this. And make this 1. Yes? And this is 1. And this is, so 2 RA over 2 RC over RA is equal to RC squared over RA squared, RC squared over RA squared minus 1. Right? So RC over RA yes. Probably the first time I've done this right. I normally end up getting a quadratic equation. You don't want to solve the quadratic equation. Root 2 minus 1. So if this is a perfect fit, the ratio of the cation radius to the anion radius is 0.414. Okay. What happens if the radius ratio is smaller than 0.414? What can I erase? I really need a larger whiteboard. This whiteboard, it constrains me. It makes me a second-rate teacher. I need space. So what are the situations? There's one situation where and there's another situation where so this situation is RC over RA is less than 0.414 and this is RC over RA is greater than 0.414. It turns out that this is unstable. And this is stable to some extent. But it basically what you learn is octahedra when RC over RA okay, I'll write it as root 2 minus 1 is less than or equal to RC minus I less than or equal to root 3 minus 1. And that's because the next higher coordination is a cube. So and I'll show you a picture from a textbook. I'll publish a picture from your textbook in the notes for today. But all stable coordination numbers or all stable radii for a certain coordination number fall within a certain range. Okay, the root 3 minus 1 is what you get when you have a cube of anions surrounding a cation. If you have a cube of anions and you want to perfectly fit a cation in the middle, then you have root 3 minus 1 for the perfect fit. It's a little bigger than the octahedral case. So radius ratio tells you how many anions surround the cation. So what's the first rule? The first rule is that the distance between two atoms is the sum of the radii, and the number of neighbors that every cation has is determined by the radius ratio. So it's actually surprisingly powerful. You can figure out a lot of structures, and in fact, if you have tables of radii, then actually what you can do is even guess a lot of structures. Just with tables of radii, you can guess the cell parameter of sodium chloride, cell parameter of cesium chloride, and you won't be too far off. Okay? How are these radii determined? These radii are what are called empirical radii. Today, the radii that we mostly use is a guy called Shannon, or two people, Shannon and Prewitt, working for the DuPont company. They went through a lot of crystal structures and just sort of systematically went through all the atom-atom distances and said, this makes sense for the radii of these different atoms under these different conditions. So the radii are a function of what the oxidation state is, so for example, if you take an ion like manganese can take many different oxidation states, right? What are the oxidation states that manganese can take? If anyone's a chemist here, they should tell me. You don't need a periodic table. Just guess. It's in the middle of the periodic table.
I know permanganate is a thing.
Yes, permanganate is what?
So
it's
plus
7. But close. KMNO4 is plus 7. So manganese goes from 2 to 7. Plus 2, plus 3, plus 4. It sort of skips 5 and 6. 5 and 6 are not common. But 2, 3, 4, and 7 are not uncommon. So as you go from 2 to 7, the manganese ion is getting smaller and smaller. So when you look at these tables, it will tell you what the radius is, given the charge and given the number of neighbors, given the coordination number. Okay? Also in manganese, if you take an ion like manganese 3 plus, it has 4 d electrons, and the manganese 3 plus can be in two different kinds of spin states. It can be high spin or low spin. Low spin is usually smaller than high spin. So if you look at manganese, you'll see like not one radius, but like 8 or 9 different radii for different oxidation states, different coordination numbers. So if you look up the radii tables, you can already guess what the structure is going to look like. Okay? Rule 1. That's rule 1. Relatively simple, the radius ratio rule. I won't expect you to remember the rules. But if I give you the rule, I'll say, how will you apply this rule? I'll give you the rule and say, how will you apply it to this situation? Okay? Are we ready for rule 2? Rule 2 is actually beautiful. It's called the electrostatic valence rule. And the most simple way to express the rule is to use graphs. Right? Graphs as in graph theory. You know what graphs are in graph theory? I love this rule. Because you know what this rule is? This rule is Kirchhoff's law applied to electrical circuits. Have any of you done electrical circuits at any level? Have you come across something called Kirchhoff's law? It's just a way of counting the current, right? We will do this for structures. Okay? We will do this for structures, and I love doing this. It's like one of my favorite things in the world to do. Let's take some simple structures. I'm going to actually, because I haven't taught you the structures, I'm going to tell you what those structures look like, okay, already in advance. Cesium chloride is 8-8 coordination, and cesium's +1, chloride's -1. Cesium has 8 neighbors, chloride has 8 neighbors. Sodium chloride is 6-6. Strontium oxide is 6-6. Zinc oxide is 4-4, meaning each zinc has, okay, the so A, B, N, N is number of neighbors. Okay? So for all these structures, what you can do is draw a graph. Do you know what a graph is in mathematics? A graph is just nodes and their connections, right? A graph is if you have a number of rivers in a city, those rivers have bridges. If you want to travel over all those bridges, you draw yourself a map that connects all the bridges, right? Imagine that the bridges are nodes, and imagine that all the connecting lines, the roads, are the links, are the connectors. Okay. But you can also look at a graph of a molecule. A graph of the methane molecule is one carbon, that is one carbon node connected to 4 hydrogen nodes. And a graph is just a connectivity. So it was not going to give you a 3-dimensional geometry. It's just going to give you how many connections there are. And these connections should not be mistaken for chemical bonds. Okay? They're not chemical bonds, even though we will draw lines. So the graph for cesium chloride looks like this. CS, Cl, 1, 2, 3, 4, 5, 6, 7, 8. For sodium chloride, looks like 1, 2, 3, 4, 5, 6. For zinc oxide, it looks like 1, 2, 3, 4. For strontium oxide, it looks like sodium chloride. 1, 2, 3, 4, 5, 6. Okay? So each strontium has 6 oxygen neighbors. Each oxygen has 6 strontium neighbors, vice versa. When I show you the structures, so these are all, these two are sodium chloride structures, NaCl structure. This structure, which I'll show you, is called Woodside, and this structure is called the CSCl structure. They're all different. What Pauling's rule says, and it may sound so simple, it's almost like saying the distance between atoms is the sum of the radii. It sounds so simple that you may say, why are you bothering to tell me this? But Pauling's rule says the number of electrons going out of the cations on these graph lines should match the number of electrons that the anion wants. Right? So each of these, so cesium is 1 plus, each of these is 1/8 plus. Correct? 8 times 1/8 is 1, and the chloride is happy. Sodium, each of these is 1/6. 6 times 1/6 is 1, and the chloride is happy. Each of these, zinc is 2 plus, each of these is 2 plus over 4. 4 times 2 plus over 4 is 2, and oxygen is happy to take 2 electrons from zinc. Strontium is 2 plus, each of those lines is 2 over 6. So 6 times 2 over 6 is 2 again, and the oxygen is happy. You may say, why are you bothering to show us this? Are you going to say that? Who's going to say that? Who's going to say that? Somebody please say that. This is stupid. No? You guys are too polite? Okay, but let's look at calcium fluoride. Let's look at calcium fluoride. Calcium is 2 plus, and fluoride is 1 minus. So it's a 1:2 ratio now. And if you look at the structure of calcium fluoride, it looks like this. What does this tell you? Each calcium is 8 coordinate in fluorine, and each fluorine is 4 coordinate with calcium. Right? It actually determines the structure type. And you know what else takes on the structure? Ceria. It's a very important compound. Actually, if you're, ceria also does this. So ceria looks like this. Okay. And but this time, it is 4 plus over 8, and 4 plus over 8 times 4 is 2. Sorry, yeah, 4 plus over 8 times 4 is 2. So each oxygen gets 2 charges. So in all of these cases, now let's look at my favorite example. What's my favorite compound? I'm waiting. And let's take SrTiO3, which is an example of a perovskite. How do I write SrTiO3? How do I write the graph? Well, think about this. Think about this. Is the strontium going to be connected to the titanium? Is the strontium going to have the titanium as a near neighbor in an oxide? Or would the strontium prefer to connect to the oxygen and the titanium also to the oxygen? That'd be preferable, right? Cations like anions and anions like cations. So you draw the graph like this. Oxygen, 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 titanium, or let's put strontium here. Let's put strontium here, and let's put titanium here. So in the perovskite, if you look at radius ratio rules, titanium will say, I want to be octahedral. So each titanium has 6 oxygen neighbors. 1, 2, 3, 4, 5, 6. Right? Titanium 4 plus. So each of these is 4 plus over 6. Okay. So each oxygen, so now I want you to tell me each oxygen is getting a charge of 8 plus over 6. Correct? Each oxygen is getting 2 of those from each titanium. So titanium 4 plus is divided 6 ways. So each of those links is 4 over 6 or 2 over 3. And the oxygen, each oxygen gets 2 of those. So each oxygen gets, from titanium, it gets 4 over 3 charges. So it has to get charges from the strontium. How do you think it's connected to the strontium? The strontium is actually 12 coordinate. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And each of these, of course, strontium is 2 plus. So each of these is 2 plus over 12. 2 plus over, so for each oxygen, 2 plus over 12 times 4 plus 4 plus over 6 times 2 is equal to 2. So the oxygen gets its 2 electrons from each oxygen being 4 connected to strontium and 2 connected to titanium. I don't know about you, but I get quite excited by this. Okay? It's just, I think, very elegant. And it's particularly elegant if you do it with this graph theoretical representation. Right? When these kinds of rules fail, it's because you have unusual stuff going on. For example, you can make the compound titanium nitride, TiN. TiN, if you work it out, you can't do titanium is 4 plus, nitrogen is 3 minus. You should not have a 1:1 combination of titanium and nitrogen. The reason you do is because it's not a salt. In fact, it's metallic. It's a pretty good metal. Titanium nitride is extremely electrically conducting because it's got a free electron floating around. Titanium behaves like it's 3 plus with an electron. And that electron floats around the structure. Right? So when these rules fail, it means you don't have a salt. Something else is happening. So can I assume that all of you understand the electrostatic valence rule, that the number of charges coming out of the cations must equal the number of charges that the anion wants? Okay, if you have a fluorine and if you have two electrons going to it, you know that fluorine is not going to be happy. This is not can be quite an exciting exercise in the crystallography of certain kinds of compounds. If you have, for example, a compound that has both oxygen and hydroxyl, O and OH, and there are, for example, very famously rust. You know what I mean by rust? Iron oxidizing. A lot of rust is actually lepidochrosite, which is an iron oxide hydroxide. It has the formula FeOOH in the early stages. FeOOH. If I do an X-ray diffraction experiment on FeOOH, I see oxygen, I see iron. Do I see the hydrogens? Is hydrogen easy to see with X-ray diffraction? Do you know? X-rays get scattered by the electrons in a crystal, and the strength of the scattering goes as the square of the atomic number. So oxygen, which has 8 electrons, actually is 64 times easier to see than hydrogen, which only has 1 electron. So in X-ray diffraction experiments, hydrogen is usually pretty hard to see. What does this mean? This means you can't distinguish oxygen from hydroxyl quite often. So when you, however, do the electrostatic valence sums, you find that each oxygen, some of those oxygens, don't get 2 charges, they get only 1. So there must be a hydrogen stuck to that oxygen, right? So you can use these rules quite effectively. But the nicest thing about these rules is you can very quickly check a crystal structure. Does this make sense? Or is Pauling's second rule violated? Are the charges not making sense, right? And by the way, I'm going to give you a set of slides on the structures of all these things, and you can look at them. And in that set of slides, I've drawn a lot of these graphs. So you can also just verify against the structure that the graph makes sense. Okay? So Pauling's second rule. What is Pauling's third rule? Pauling's third rule talks about the cost of sharing features. It talks about the cost of sharing features. The third and the fourth rule. I don't know why Pauling decided he needed 2 different rules for this, but it's the cost of sharing features, and I'll tell you what this means. So I'll summarize it as Pauling's third and fourth rule. Okay, if I take the structure of silica, sand, also the nature of SiO2 and window glass, I find that silicon is 4-coordinate with oxygen. Each silicon has 4 oxygen neighbors. So silicon forms a tetrahedron, right? Each oxygen is shared with 4 other silicas. 2 other silicas. So again, if I write out the electrostatic valence, it's silicon 4 plus, 1, 2, 3, 4, O, O, right? 4 plus over 2, 4 plus over 4, 4 plus over 4 because they're 1, 2, 3, 4, and 2 times 4 plus over 4 is 2. So this oxygen is corner shared. Corner shared. It's called polyhedral corner sharing. But in some other structure, you might have 2 oxygens in the tetrahedron. So that's a tetrahedron. So let's say this is M. That's a tetrahedron. And you might have 2 oxygens sharing features. Oh, that's one tetrahedron, and this is another tetrahedron. This is called edge shade. This is another structure. In some other structure, you may have edge shade tetrahedra. I hope you see this is the corner and this is the edge. So two oxygens are sharing. In yet another structure, you may decide to share faces. You might have three oxygens. I'll draw them like this. Three oxygens forming a face. A fourth oxygen here, a fifth oxygen here, M here, M here. You see these M's are, in both cases, these M's are tetrahedral. But here, there's a face of three oxygens that are shared. Face shared. Now, Pauling said, as you go from corner shared to edge shared to face shared, the crystal gets, now you have to tell me, happier or less happy? Corner versus face versus edge versus face. Is the crystal more happy or less happy? You want a hint?
Less.
Less. Why do you say less? You don't need a hint. Great.
Context on the board. Is it cost?
Yeah, okay, good guess. But now give me the physical reason. A hint. Does the M have a charge?
I think it's the electron sharing.
It's not about electron sharing. This is just electrostatics. Okay, this is just ionics. Does the M have a charge? Is it M, say M something plus? Okay. What do you see going from corner to face, to edge to face? What's happening to the M?
Oh, they're getting closer.
They're getting closer. Do the M's want to do that? No. Okay, that's simple. That's Pauling's third rule, that sharing of features is expensive. Cost of sharing, okay? Okay, sharing is avoided. If the structure can avoid sharing, sharing is avoided. Okay, in fact, I don't know of a single structure of silica where you have edge sharing of SiO4. I don't know a single structure. It's always corner sharing. Okay, here's the fifth rule. The fifth rule says, and I don't like this fifth rule because it's like a tongue twister, but it says that if the charge on the metal is high and the coordination number is low, the cost of sharing becomes intolerable. It becomes too high. So if you have a high charge ion like silicon and low coordination number like a tetrahedron, 4 coordinate, then it really doesn't want to share. If you have a low charge ion, say like cesium in cesium chloride, and a high coordination number, it's 8 in cesium chloride, then sharing is okay. See, I'll show you. In cesium chloride, there is edge sharing, but it's the edge sharing of, there is phase sharing, but it's a phase sharing of cubes. Okay, so cesium chloride says, I don't mind, but phase sharing. Okay, in the rock salt structure, there is edge sharing, but the rock salt structure is 6 coordinate. And the charges are rarely above 2 plus, 2 minus. Okay? So the Pauling's fourth rule is a bit of a tongue twister. That's why I like to call it the third rule. So sharing of features is a no-no when cation charge is high and coordination number is low. believe it or not, using these first 4 rules, you can give me a chemical formula of an oxide and I can probably guess roughly what the structure looks like. Okay, just using these 4 rules and using about 35 years of experience. But never mind the 35 years of experience. Okay? Now, right, we are ready for the 5th and final rule of Pauling. And this is actually a very interesting rule. The 5th rule is called the rule of parsimony. Rule of parsimony. That structures tend to be, the structures of ionic crystals tend to be as simple as they can possibly be. Simplest structures preferred. Do you know what this is called in philosophy? Who's taken a philosophy class? The simpler the structure, the more preferred it is. Do you know what this is called in philosophy? Have you ever heard people talk of something called Occam's razor? Anyway, that's what it's called in philosophy. That if you have a simple way of saying something, it's preferred to a more complex way. The exact statement of Occam's razor, sometimes people also write it as OKHAM. And the precise statement of that is plurality must not be posited without necessity. Okay? Nobody's taken a philosophy class? Have you taken a Latin class? Has anyone taken a Latin class? Nobody's taken a Latin class? So then I don't need to tell you that Occam said, pluralitas non est ponenda sine necessitate. By the way, I've never taken a Latin class. But there it is. Great. So those are Pauling's rules. Okay? Now, that took a long time, but it's probably worth it. And again, these rules are not rules. Rules don't mean they can't be broken. These are not laws. These are not like Newton's laws. Okay? These are not like the laws of thermodynamics. These are really guiding principles for how ionic structures form. And it's remarkable that he already had them laid out by 1928. Because remember, the Bragg law paper was only like 1912 or something. So between 1912 and 1914, there'd been enough diffraction done on crystals that Pauling could look at a lot of crystals and says, here's what I think is happening. These rules are being followed. Right? Pretty remarkable. Right? So in the year of the Lord 2023 or whatever, if you write a paper saying Pauling's rules don't work, I'm not impressed. Okay? Or as the words of the song go, that ain't impressed me much. No? That ain't. What's the song? I don't think any of you know Shania Twain. Do you know Shania Twain? No? Do you know Bad Bunny? Actually, I have to say I don't. Do you know Daddy? I know Daddy Yankee, but I don't know Bad Bunny. Okay. So, we are ready for some structures. And now I need you guys to pull out your space group tables. So pull out your space group tables. And let's start looking at some crystal structures. By the way, there's one concept. I'll put these notes up. There's one concept which I've not talked about, and it's called bond valence, but it'll be in a set of PowerPoint slides that I'll present. So let's look at sodium chloride now. Okay? So I'll put these notes. These notes are not published yet. I'll put them up. But here's NaCl. And remember, when I say sodium chloride, it's representative. This is the mineral that people solved the structure for. In fact, I think I've mentioned this briefly, but the structure of sodium chloride was known even before there was X-ray diffraction. Okay? How did people know the structure of sodium chloride? Because they could measure the density. They could measure the number of sodiums and chlorines. And they knew the atomic masses of sodium and chlorine. And they knew that no other structure is compatible. Right? So sodium chloride, the space group is Fm3 bar m. It's a space group of copper, which, as you may remember, is written is F4 by m, 3 bar, 2 by m, 2 by m. And we've gone through some of these notations in the past. And it's number 225. So it's cubic, so you need a cell parameter. It's 5.63 angstroms. And then you have sodium at 0, 0, 0, which if you look at your space group, it's 4a. And chloride at 4b, it's half, half, half. Right? And if you pull out your space group tables, you may remember that 4a and 4b have nothing next to them. There is no symmetry operation that makes more replicas. No, go to the next page where it says 4a, 4b, right? And when you do that, you see there is nothing within the space group that says 0, 0, 0 means also somewhere else, right? But why is it 4? What makes it 4? See, this is why I don't like missing a week. Why does it become 4a for the space group?
Is it because you can rotate it?
No, 4a means there are 4 sodiums in the unit cell. Where does that 4 come from? It comes from this, right? What does that mean? Which means every atom at 0, 0, 0 also becomes an atom at? Exactly. Right? We've done this at least 2 times because we did this when we studied copper. We also did this when we studied silicon. And then these things are also added here. Yes? Phase centering. It comes from the phase centering operation. So there are 4 sodiums in the unit cell and 4 chlorides in the unit cell. So we know how to draw this in sections. Here's the z is equal to 0 is equal to 1 section. And here's 0 is equal to 1/2 section. So here are all the sodiums. It's just FCC. Right? Should I go through all of the chloride positions, or can you guess where they sit? Can any of you guess where they sit? Remember, every sodium has 6 chloride neighbors, and every chloride has 6 sodium neighbors. And I put sodium at 0, 0, 0 and chloride at half, 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 but I can also flip them around and put chloride at 0, 0, 0 and sodium at half, half, half. With this information, please tell me where I should draw the chlorides. Always symmetry. Any guesses? Or should we work it out explicitly? What's your preference? Okay, I'll give you a hint. 0, 0, half. 0, 0, 0, 0, half here. You said here, 0, 0, half? That'd be correct. Yeah. Okay, let's put half, half, half. Let's put half, half, half. Let's put half, half. Let's put the chloride there at half, half, half. Let's put the chloride here at half, half, half. And then you can try and guess the rest. This is this half, 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 right? Do you want to guess now where the other chlorides go? They go here, 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 and here. You see why I wanted you to guess? What do you see now? Do you see the blacks at 0 are equal to the reds at 1/2 and vice versa? There's perfect symmetry, right? So if we draw the structure in a more 3-dimensional sense, and I'm very brave, so I can do it. You see why I prefer to show you structures like this over structures like this. Okay? How many neighbors does each sodium have? Look at this sodium, neighbor 1, neighbor 2, neighbor 3, neighbor 4, neighbor 5, and 1 below, 6. Chloride would be the identical. You get the 6 neighbors? And if you actually draw out the polyhedra, you'll see the polyhedra are edge shared in this case. Okay? With this information, can you tell me the density of sodium chloride? You have the unit cell. You know that there are 4 sodiums and 4 chlorides that sit in a space of 5.63 angstroms, the whole cubed. So you have the volume, and you can get the mass of a sodium and a chlorine multiplied by 4, and you can calculate the density. In the space group tables, I told you that these are the positions of the sodium and the chloride atoms. How do you know that those are the positions? How do we know that those are the positions in the space group tables? Where is that information from? Where is the information that sodium goes at 0, 0, 0 and chloride goes at half, half, half? Where does that information come from? Does it come from the space group tables? No. It comes from X-ray experiments, right? And by the way, if you guys play with X-ray diffractometers, who's used an X-ray diffractometer here? You have? You have? Have you? You know, one of the funny things you'll find, if you ever record the X-ray diffraction of sodium chloride, you come back after an hour, and where the X-rays have fallen on the sodium chloride, it'll be like bluish black. Because X-rays somehow, lab X-rays, create like Schottky and Frenkel defects in sodium chlorides. They create cation-anion vacancies and so on. So you can actually use it as a detector of X-rays. It doesn't make a difference to the experiment because it's a very small amount of material that gets converted. And then, of course, if you leave it for a while, you come back and becomes a white salt again. It repairs itself. Sodium chloride, extremely important structure. And what you see in the structure is what I've already told you in the past. It looks like a 3-dimensional chessboard, right? It looks like this is a 2-dimensional chess set. Here are, for example, here's the white square and here's the black square. This is in 2D and in 3D. It's like a 3-dimensional chess set. So it's a very common motif in a lot of things. In magnetism and crystallography, in structures, it's an extremely common motif. And many, many structures are derived from the structure. We've already looked at the structure when we were looking at the Madelung, when we're calculating the Madelung potential, right? +1, -1. Yeah. Okay, good. Next, the cesium chloride structure. And this is actually in some ways even simpler. If you go to cesium chloride, the space group is now PM3 bar M. PM3 bar M. And where did we see the space group? Actually, let me do it in the other way. Let me put Cl at 1A and Cs at 1B. And the cell parameter is 4.11 angstroms. Do you have your space group tables opened? What does it say? You see that there is no symmetry that takes the 0, 0, 0 position to anywhere else, or the half, half, half position to anywhere else. And there is also no centering in the space group because it's P. So 1 remains 1. Only one cesium atom in the unit cell and one chloride atom in the unit cell. So I'm not even going to bother to draw it in sections because I can draw the structure like with cesium there in the middle. And okay. So again, this is 8 coordinate. And going from cesium chloride to sodium chloride, from sodium chloride to cesium chloride, this is a beautiful illustration of the radius ratio rule. Cesium is too small to sit in 6 coordination. So it says, I need more neighbors. So it prefers to have 8 coordination. Right? And if you look at the next cesium chloride cell, you see that these 4 chlorides form a face that is shared between 2 cells. So the polyhedron is the cube, and these cubes are face sharing. But cesium just has a 1+ charge, so it says, I'm fine, I don't mind. I don't mind face sharing because the charge is low. Okay? Is there another name for this structure? Do we call this something else? Do you remember the structure of alpha iron? Alpha iron we said was body-centered cubic, right? This is not body-centered cubic because body-centered cubic means it's the same atom at the corner and the middle. Here these are different atoms at the corner and the middle. Okay, so don't call this body-centered cubic. Okay? Let's go to the structure of zinc blend. And now you have to tell me whether you can find the space group in your notes. It's F4 bar 3M, number 216. Please see if you can find 216. Any questions about these 2 structures? No questions, right? Let's go to zinc blend, 216. Space group number 216. Again, it's cubic. It's F4 bar. 4 bar, I believe it's F4 bar 3 2 by M. So 4 bar, you may remember, is a 4-fold axis, is a rotation by 90 degrees and an inversion. Okay, and the cell it's again a cubic space group. The cell parameter is 5.41 angstroms. So you have zinc at 0, 0, 0. I believe this is 4A. And sulfur at quarter, quarter, quarter. And this may be something like 4C. Can you tell me? Do you find this? 216.
Oh, page 216.
No, the space group number 216. It's not page 216. Remember, I also gave you. No, you found it. Did you find it, Josephine?
Yeah.
Can you tell me what 4A, 0, 0, 0, 0, 0 is 4A, right?
Yeah.
And quarter, quarter, quarter is?
It's
4C. Lovely. 4C. So again, it's got this F. So F centering. And it's this F centering which gives you this force. There are four zincs and 4 sulfurs in the unit cell. Because of the 0, 0, 0, 0 becomes half, half, 0, half, 0, half, 0, half, half. And you have to do the same addition here. So let's actually do that. So I'm going to add, so half, half, 0, half, 0, half, 0, half, half. I'm going to add it to this. So half 0, 0 will become 3/4, 3/4, 0. Half 0, half will become a 3/4, 1/4, 1/2, 1/4, or 1/2. And then 0 half half becomes 1/4, 3/4. Oh, sorry. I made a mistake. Oh, yeah. 3/4, 3/4, 1/4. There's, okay, good. Half half, 0 plus this is 3/4, 3/4, 1/4. Half 0 half is 3/4, 1/4, 3/4. And then 0 half half is 1/4, 3/4, 1/4. So, no, 3/4. So I have 2 at 3/4, 2 at 1/4. So I'm ready to draw the structure. So first I'm going to draw, so I need 4 sections. First, I'm going to put in my zinc. My zinc is just FCC zinc, so I know how to do that. That's FCC zinc. By now, this should be very familiar. By the way, be assured that you should know FCC for your midterm next Wednesday. Okay, it's like so ubiquitous that if you don't know FCC, it doesn't allow me to ask anything else. So FCC, you have to know. Without I just should tell you draw FCC, you have to be able to draw it. So that's FCC for zinc. Let's put the sulfurs in. 1/4, 1/4, 1/4 is here. 3/4, 3/4, 1/4 is there. So check that. And then we have 3/4, 1/4, 3/4, and 1/4, 3/4, 3/4. So 3/4, check that and check that. That is the crystal structure of zinc blend. Does the structure remind you of anything? If the red and the green atoms were the same, what would that structure be? Do you remember? Very good, diamond. So this is a great example of what is called a group-subgroup relation. Imagine going into the diamond structure with 2 different cans of paint and 2 different paint brushes, because you don't want to mix your paint brushes. And imagine painting every gray atom alternately green, red, green, red, green, red, so that the green atoms only have red atom neighbors and the red atoms only have green atom neighbors. So this is the relationship between silicon and gallium arsenide, or silicon and indium antimonide. This is, if you understand this group-subgroup relations, you understand all semiconductors. I'll show you that in a minute. But every zinc has 4 sulfur neighbors. For example, it has these 2 on top and these 2 below. And every sulfur has 4 zinc neighbors. If you take this sulfur, its neighbors are this and this and this and this. Okay, so this is a structure also where you can write the structure, the graph for the structure will be Zn S 1, 2, 3, 4, 4 plus, sorry, 2 plus, 2 minus. Okay, now let me ask you a question. If you look at the Z is equal to 0 layer or the Z is equal to 1/2 layer, you easily see the FCC arrangement, correct? If you see the Z is equal to 1/4 layer, does that look like FCC to you? No. It has to be FCC. So let's do something. Let's take that layer and tile it. Atom here, 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 and voila. Does that look like FCC? So it's just an FCC sublattice that's shifted by 1 quarter, 1 quarter, 1 quarter. So 0, 0, 0, 0, 0 and 1 quarter, 1 quarter, 1 quarter are the origins of two independent FCC sublattices, one containing the cation and the other containing the anion, and you can change them around. And you end up getting a structure where every atom is 4 coordinate. Okay, forming tetrahedron. So again, let's go through the relationship between, this is an important thing for all semiconductors, because if you look at carbon, silicon, germanium, tin, lead, these are all semiconductors with the diamond structure, and they all have 4 electrons per atom on average, right? Or 8 electrons per pair of atoms. But you can get this 8 electrons in other ways. For example, zinc has 2 valence electrons, and sulfur has 6 valence electrons. 2 plus 6 is 8. If you had gallium arsenide, gallium has 3 and arsenic has 5. 3 plus 5 is 8. Okay? So you go from the parent structure, which is diamond, to the zinc blende structure just by alternating the atoms. In terms of expressing the structure, you go from the FD3 bar M space group, where you have only one atom that becomes another atom in the unit cell of the same kind, to F4 bar 3M, where the two sublattices are separated by 1 quarter, 1 quarter, 1 quarter. Is all this making sense? So in the next class, I'll go through the rest of the structures, and by that time I'd have also posted more notes, and you probably will, I'll post a assignment today which will probably be 100% Vesta based assignment. You have to draw structures, many of these structures, okay? And you can also then see, I would encourage you to not just draw the structure, play around a little bit with it, okay? And Vesta is, if you're a materials researcher of any kind, Vesta is going to serve you in very good stead for your entire career. It's also free. When I started here at UCSB, I didn't have anything like